I'm delighted to introduce our first speakers, Professor Saulius. Saulius has physics and material science training. His current interests are in the fields of nanotechnology and light matter interactions occurring in small space and time domains. In 2011, he established and now directs a multi-user nanotechnology facility at Swinburne. It was open to the users as one of the Australian National Fabrication Facility ANFF labs. His talk is on optical hydrogen sensing. Thanks, Saulius. Welcome.
Yeah, thank you very much for invitation. It's great to be here, and I have opportunity to speak at conference. So it's 2 years we were not doing this, and it was another challenge to put up slides for slower research years. This topic is slightly out of our direct kind of research in what light is doing on nanoscale, but it's very, very close. And we keep eye what is happening in this field. So I will start from introducing optical sensors as we understand them, how we localize light using surface enhanced techniques, Raman scattering or infrared absorption. So we can squeeze light with nanoparticles. Now it's popular topic, metamaterials, and we can actually use them also for hydrogen sensing. I will show you. And something very recent, I think this is this month, we showed that actually you can realize situation when you have strong light matter interactions. So it's quantum optics. Suddenly we can have Rabi splitting of your absorption lines. And then finally, a little bit of what we are sensing, how we are producing hydrogen, but this is not really into the details, but just challenging that we really need to know what species we are looking after on the surfaces. So we looked at solar hydrogen field. It's really booming. It's difficult to catch up if you are not directly in that field. And our angle was to see what is the efficiency. It's fantastic photocatalysis catalysts are produced, but can they compete with something very, very simple? So you have solar roof with the most efficient or cheap silicon solar cells. You put electrodes which are already established in water, and you split water. And this is actually a very efficient way of producing hydrogen. We made some small, simple 1% efficient solar cells just by placing nickel film on silicon. And this is somewhere, actually in March on our campus. These are my hands. We make some simple solar cell and we split water. We use the efficiencies. And definitely we need to have good sensors if we are producing hydrogen, especially efficiently. So optical sensors is another vast field and booming, as Sally mentioned. Bio applications are very, very strong. So what is key for that field, especially for bio, is label-free. So you don't need any labeling. You can detect your species you want to see on the surface by very different techniques. Surface wave, nanoparticles, nanocarbon tube, gold particles, some strange resonators, and photonic crystals. This is from the review paper, and this is the cool application when you have laser, and laser is changing wavelengths. It's very easy to detect. And look here, the cost is very low because you can really go to foundry, which is making silicon, or this is not silicon, but you make semiconductor materials. It's readily available and it's wafer scaling. And sensitivities, which usually you need to achieve, quite high. So what we like in this approach that everything is based here on physics and nanotechnology, rather than on chemistry, which is not our strength. And we know what we should reach. We need to go to picofemtomolar sensitivities. And if we compare with the labeling methods, they actually work slightly less, for less sensitive, so to speak. So there is a big potential with the optical sensors. So what we need to do, we need to detect something with light. We need really to create place where the interaction is strong. How to do that? Nanoparticles is a good invitation for this. We can squeeze light, create high intensity, and then everything which is in that place will experience absorption or scattering, which we can detect. So at the time, we had a tool which can define single exposure site on resist better than 1 nanometer. So we asked ourselves how strongly we can squeeze light using nano-gaps. And this was time ago. If you calculate with the numerical modeling, you will get some crazy numbers, and it depends a little bit of your meshing and the shape, and shapes are always perfect. And in reality, you have slightly different particles. And actually, this research was focused on creating nanoparticle of gold, which can be emitting light. It's luminescent because we have so high intensity in gold, and it's not bleaching in biomedical applications. But okay, the question is how to put light on nanoscale and what intensity you can reach. So we fabricated arrays of nanoparticles, and it's standard Raman setup. You have laser, you excite, this was water solution, and then you have detection. This is your Raman scattering of molecules. We chose the smallest we can find, so 1 benzene ring, so to speak, it's really small. What you can see that the Raman intensity is really highest when you have very, very small gaps. So this is 3.5 nanometers, and it's not single particles, so it's array of particles. And this is definitely working for the nano-gap, because for this polarization, vertical here, you have the signal. But if you make it polarization linear in this direction, you have much lower, because you only have some enhancement on the corners. Okay, so then if I will take molecules which have some extra 2 benzene rings, they are larger. So how to sense them? And this is everything label free. So I have just solution of that material. So I can actually see that I need a larger gap to have the strongest Raman signal. If I measure simply optical properties, which is extinction, this is total losses in absorption and in scattering, I see that those arrays actually have very strong scattering properties. So if you see when particles are joined together, so this would be black line, and then you have very big difference if you get just changing nanometers, because those particles are talking to each other. When they are far away, they are not interacting, so then your extinction spectra, this is how light is scattered and absorbed, moves to the left side. When you measure Raman, you are sensitive to how much light is excited at the wavelengths of your laser and at the Stokes wavelengths of your molecules. So you are sensitive to these 2 points, and they can be everywhere if you engineer the gaps. Well, so what is the enhancement I can reach? And this enhancement, if you look at the numbers, is not very, very large, because I think this is enhancement, which is practical enhancement. I have focal spot in water solution of that dye, and I know how many molecules I have in the focal spot, and this is just in solution. And then I compare, this is my reference, and then I focus the same beam with the same optics on the array of nanoparticles. What I can get, this would be that enhancement. It can reach roughly 6,000 times. Now, if I'm calculating how many molecules are in those nano-gaps, how many of them I have, then I will get those crazy numbers, 10 to the power 9 and 10 to the power 10. But reality for real application, this is what you are getting. You are focusing your light. When you see enhancement on the surface, it's thousands. And probably it's good to say that if I have gaps somewhere in this region around 10, 20 nanometer, it's really good enough. I'm not going to this crazy small gaps. So the goal finally is to have surfaces with the gaps around 10, 20 for label-free sensing. So I will not go into details, but then we looked what kind of particles, their sizes, their pairs, their shapes, how this depends on how surface enhanced Raman scattering depends on this. What we found, actually, if you introduce by fabrication, it's not with the protocol, you introduce some randomness. Is it better? And the answer is yes. So you have 2-3 times better surface enhanced Raman signals, usually when you have random particles. Once it's random, yeah, it's good invitation. We know how to make random surfaces, and it's very easy. You don't need lithography and crazy resolutions. We work with the silicon. We making it black by plasma etching. You can really do anything on silicon surface, really to the nanoscale. So randomness is, if it is good, it's easy invitation to make large area sensors. And we did this over the years. Collaboration was also here with the Saulius group. We look for surfaces which we ablate with laser. The same black silicon I showed before, we coat with the gold, and it's your sensor. This is commercialized in Brisbane. This is just oxidation of copper. It's probably the cheapest sensor on the market. And then you can do actually something very interesting. You sputter gold on film of plastic, put into micro oven for 150 centigrades, and you have this nano surface. And the roughness, you can actually control how much gold you put on the surface. So it's simplest sensor possible. So randomness is good. We can produce surfaces which are good for surface enhanced Raman. So this was kind of scattering based approaches. What we also like, which is more definite, is absorption based approaches in sensing, which usually you measure in transmission. And all of them are linked, yes? So it's everything comes to the conservation of energy. It's one. So now it's hydrogen sensing. We need good materials, so we are using palladium gold, nanofilms. We are choosing wavelengths of light, which is in telecom. So technically, this technique can be put on chip. We are mixing gases, and we're measuring transmission. So, but it's plotted here, it's extinction, it's -10 logarithm of transmission. And you see that hydrogen is on and off, making changes in time. So we are measuring transmission. We have benefit of exponential part. So this is imaginary part of refractive index is losses. So its exponential function is always good. And in transmission, we are more sensitive than in reflection, but you can measure both. How to prepare those films and alloys? It's a very simple technique. You co-sputter them, or you can sputter one and the other one and make layered structures. Then you can anneal your substrate afterwards, or you can actually sputter on a hot substrate. If it is hot substrate, you can see that if we are mixing gold and palladium, co-sputtering together, we have full control, and the phase alloying very nicely. If it is layer by layer, this is also something what you can expect and calculate from multi-layer XRD, X-ray diffraction pattern. So we know how to produce those alloys. And this is how they perform optically. And here, let's look. This is not infrared. It's visible range. And this is a pure palladium. So palladium is good for hydrogen sensing because when pressures are equal, let's say 1 bar, we can see the changes of permittivity, real part, imaginary part. So this is refractive index square. So the changes is measurable. And numbers are large, so it's good invitation to use it for sensor. So here, what you see how your transmission is changing in visible range for different thicknesses of sample. And this is typical thicknesses I'm speaking in here. Well, if we look how much transmission is changing, when I sputter gold and palladium, at room temperature, it looks like very strong extinction changes with the thickness, but actually, they are less sensitive in terms of uptake and release of hydrogen. This is time now, different thicknesses. Those co-sputtered on cold substrate, those films are very slow. What we need for detection of hydrogen, usually industry asking 10 seconds, because this is the timing they're using in many sensing techniques for 4%, which is starting to be dangerous. And we can reach, for some of our co-sputtered and annealed films, we can reach really tens of nanoseconds with this technique. What else? We found that sometimes it was happening randomly at some thickness, film is suddenly becomes from mirror changing into scattering surface. But you can do this in fully controlled manner. So you expose hydrogen overexposure. So it's 100%. This was done in Japan. They're saying 100% hydrogen is absolutely safe. There is no oxygen, so it's they can work there in full control. If you're more safe, you are working with 4% of hydrogen, you need a little bit more time, but this will happen. So your film, if you look at the film from the top and from the bottom, you see that entire film is actually cracked. This is SEM exactly corresponding to this situation. Now, what is happening with optical response? So I measure my optical losses in transmission. If I just fabricate film and spot it, it's black. So I see that it's hydrogen sensitive, recovery time is longer than uptake time. But when I make this overexposure, when I have the nanoscale cracks, actually it's a larger extinction range and it's faster. So it's good to use for sensors. When it begins to be more fast, our question is always to reach those 10-second response time. This is around 60% of palladium in the film. We had opportunity to see what is happening with the swelling of lattice when hydrogen comes in, and this is XRD during hydrogenation. So you see that hydrogen is expanding lattice. But after that exposure, we have cracked film is actually expanding more. So this is recalculated to the lattice distances. So the picture, what is happening on that surface, once hydrogen enters, surface swells and then forms cracks. And those cracks actually good for sensing. What we also found, and COVID helped us, some samples were on the shelves for too long. They have no sensitivity whatsoever. So you just take sample which you know that it should be sensitive, it's not working. Obvious approach, we annealed, and then we put in the hydrogen, and it showed some sensitivity, but we needed this 10-minute conditioning when we recovered fully functioning sensor. And I think this is happening also in any sensor. If there is metal and hydrogen, that nanocracking is happening, and it's probably important for even some nanoparticles. So it's another topic. So we finally decided that each time when we have film, we anneal it once, we condition, we can call aging process with the hydrogen a couple of times, and then it's stable. And this is the sensor we can use. There is many things are happening here. There is absolutely reproducible results about correlations, and this is probably an invitation for further work. But it was already too many samples. So once we have the hydrogen film, you see the sensitivity, so optical losses in transmission, different hydrogen concentrations, and slopes are changing their time, uptake and release. And again, we can reach those 10 seconds which we want. This is it best sensor we made? Probably not. So what we also use laser in our research. So we thought it's even easier. You don't need vacuum sputtering. You just put powders of metal and tungsten oxide, press into tablet, ablate with the simplest laser you can find, and you transfer on the substrate. You have nanoparticles and kind of loose film, and we use it for sensing. So these are different ratios of palladium to tungsten. What you can actually see is it's a good result that from 1% of, it's not palladium, this is platinum in this sputtering case, we see that it begins to be very fast reaction time with the hydrogen. When it is a smaller concentration, it's more difficult. But this kind of shows like no sensitivity, but sensitivity exists, so it's shown here, but the time is fast. Next, what we want to do, to use also Chris' machine in his lab, is actually to see how the color is changing, because this is color sensor. If you have hydrogenation, you have this Ukrainian flag colors changing from yellow to blue. So this is an invitation to continue. Okay, so now I have many slides, so I run fast. Next. Topic of metamaterials. Obviously, everyone was hearing about them. So what is popular is metal, then dielectric, insulator, and metal. This is usually very thick film. Thickest for optics, it's 200 nanometers. So it's absolutely no transmission in this formula. I kill transmission, then my absorption and reflection is fully related by energy conservation. So if I measure reflection, I know how much light is absorbed because there is no transmission. Gas sensing in infrared. This is vast field, and it's probably will definitely grow for much more in all the fields you can imagine. So these are gas cases. What you can appreciate that for infrared wavelengths for this fingerprinting region, you can find really, you can identify materials. And this is the same for solid or liquid states as well. Here, what I want to, with this slide, to show that you actually would like to measure spectrum very precisely, which is difficult, or you want to have the light source, which is very narrow, exactly on the material you are sensing. Okay, so we are sensing hydrogen. What to do with the metamaterials? I can make gold and palladium because they are good materials, and then I have another good material for hydrogen, which is changing phase depending how much protons I have in the system. So yttrium becomes more dielectric when it is uptaking hydrogen, and otherwise tungsten is oxide is making transition to more metal state. This is obvious from the balance. Just by design of the diameter of palladium dots, I actually can tune to any wavelengths I want. This in infrared range. But for sensing, it doesn't matter. I choose one size of disks. I make device, and then I put hydrogen, what is happening with reflectance. For yttrium and for tungsten, it's shown here. So if the blue line, there is no hydrogen, and then if we put hydrogen, there is change. So the summary is here, the peak shift, so the best you can measure, doing this. So for yttrium is getting more dielectric, for tungsten oxide is getting more metallic. Okay, so again, we go to the very safe conditions of 100% of hydrogen in our setup. We run hydrogen and we are reading every 4 seconds. What happens, so these are from 20 to 40, not many steps. Basically, you see the big change in reflection, if you want absorption, because they are same. 1 minus reflection is your absorption. We see big jump. For example, for case of tungsten, we switch on hydrogen, we have change happening fast, and then we see recovery. So this is release time, and in long times it comes back. So this is a fast sensor, but it's metamaterials you need usually. This is done with electron beam lithography. Again, it's too expensive for practical life. We can understand how it works. The light actually goes in that layer of below the palladium, and here where interaction is happening, and here where hydrogen protons actually are going into the phase of those two materials. We can model optically by software, so we set the real part of refractive index, and what we are changing here, it's imaginary part. This is only absorption is changing, and we see that spectrum can change. So technically, we can understand everything what is happening optically for these type of events of sensing. And sensing, again, it's very fast, which is good. Electron beam lithography, nobody likes it because it's too expensive. But in Japan, if you don't do business, you go to STEPA and it's free of charge. So we used STEPA in Tsukuba. We made the mask, which is 10 centimeter, then 5 times reduced size is 2 by 2 centimeters. We are making those metamaterials on the surface using simple stepper lithography. It's few seconds exposure for entire 8-inch wafer. So we can read in the thermodynamics books that absorbance is equal emittance. Our referees were not happy that we are measuring this because it's known for a couple of centuries, but we were still not believing. So we took sample, we heat it up, put into the same spectrometer, which we are usually measuring absorption spectra, and see how much light is emitted from our surfaces. Because we are using masks, it's easy to make negative, positive, or you are changing resist. So we can make metamaterial with the particles or with the holes. What we found, and here just mentioning this as a fact, we will see more details later. We see that each time I have reflectance, I have emission. If I'm measuring really how much black body radiation comes from my surface, they are perfectly matching, and I can control the period. I can shift where I want to have that emission. Okay, so Kirchhoff was right, so it's working. If I can create absorbing surface, and it will be my perfect emitter, can I make perfect absorber to have perfect emitter? This is next challenge we looked. And we used, again, meta surface. We placed silica In between is dielectric, because it's easy. And what we see here, how light is concentrated below a particle, and those sizes around 30, 40 nanometers, when light is really going into that dielectric layer. This is correspond to the situation where you have almost no reflectivity, so it's perfect absorption. So you have 100% of light. It's in simulations, and I will show you experiments. So when you look for scattering, absorption, and scattering and absorption cross-section, so this is where you have maximum. So here you have perfect absorber. Then our thinking from Kirchhoff's law, I have perfect emitter. What we found actually was a little bit unexpected. Everyone is using chromium to glue gold to surfaces. It's common knowledge. But in fact, what we found that 5 nanometers actually not making perfect absorber. What we needed to make much less good metal on the surface, we put 50 nanometers to have more losses, optical losses, because what is perfect absorber? It means that during optical cycle, which is femtoseconds, energy which is dissipated is equal to the energy which is coming on the sample. So it should be very fast dissipation of energy, radiation, diffusion is low, and it should be equal input, equal output. Again, some kind of Kirchhoff's law picture. So if I have 5 nanometer coating, what I actually can see that reflection and emission, so they are matching, no surprises here. But if I plot the Kirchhoff's law when emission is equal absorption, is actually here. All my samples actually too much reflective. So gold is good material for surface, but it's actually too much reflective for absorption. So when we put 50 nanometers of chromium, then we reached all samples actually converging on the Kirchhoff's law. It means I have now a recipe how to make perfect absorber. If I have perfect absorber, I should be able to make perfect emitter. And this is next part of my talk. Perfect emitter. So again, the same metamaterial. Gold, nanoparticles on top. Now it's gold and gold. Because we are not in hydrogen sensing, we don't need anything specially acting with hydrogen. So it's just a question, can we make a perfect absorber to use it as a perfect emitter? And perfect emitter, the logic is that if I have perfect emitter, I don't need any spectrometer for detection. So it's invitation for miniaturization of sensors. I can have source, which is shining known wavelengths of light. Try to do it in infrared with a very narrow band. You can't. So the best you can do is actually molecular lines, which are very narrow. So how to use those narrow lines in the perfect absorber to use it as a emitter for my sensing application. So this is kind of dream. So, but I need now to design perfect emitter. We use polyamide because polyamide is can survive at 300 centigrades. And each time for radiation, we know you need more light coming out of surface, you need to heat up your surface. So if you use different polymer, it will melt, it will change your meta surface. So we use the polyamide, which is really a robust polymer. So this is absorption spectra in infrared for polyamide. And this is our meta surface. We are changing disk diameter, top disk diameter. The period is always twice the diameter size. We have this plasmonic band, broad plasmon, which is moving with the size of particles, moving onto my region where there is absorption. So what happens? So this is experimental result. And this is a theory. Somebody was asking me why your experiment is better than theory. It's a good question. And I think in theory, you don't pay attention to any polarization and alignment. So you just have optical properties defined by permittivity. We engineered our polyamide just by putting Lorentzian lines with certain intensity. But in real life, our polyamide is probably aligned. That's why our lines are more narrow. So this is experiment. What we see that what we are measuring now reflectivity, what is most bright is has low, it's opposite sense. So it's perfect absorber. So it has low reflectivity. One reflectivity when it's all light bouncing from the mirror is actually black. So we look for perfect absorber. Well, the bright part is absorber and absorbing intensity. Plasmon is just changing position depending on geometry, which is obvious. But in experiment, we see that we recognize actually something peculiar in the spectra. There are splits. If we calculate by FDTD, which is kind of Maxwell equations, and you just launch light and you look for the result, it's also reproducible. Each time my plasmon line is hitting absorption line in material, actually have splitting. And this splitting is Rabi splitting, which is another invitation. And in textbooks you are reading when you have cavity and single atom inside cavity, and then you can solve interaction, then you have this Rabi splitting. So we had a little bit of hard life with our referees to convince that it's Rabi splitting. If we use now this surface as an emitter, again, Kirchhoff is right. So I have absorption spectra. If I measure radiation, it will be exactly matched. So the final slide from this topic is here. It's still not published, but it's more obvious what is happening. We used polyamide, which is slightly different. SU8 and another resist we use for those step lithography. What happens is exactly the same. I always see the splitting, yes, but the best is in polyamide. If we are tracing this, for example, line, what is happening? We have intensities increasing when my disks, by geometry, making the plasmon line moving through the absorption line. And you can call it surface enhanced Raman absorption, so SERAS. And then when you are very close to the line, you have splitting, which is phonoresonance, again, widely used in sensing. And then exactly on the absorption line, you have this Rabi splitting, and this is strong coupling, which I think first time we showed this in this kind of geometry. Okay, so what it means now for me. If I want to sense polyamide, I can actually use this surface to heat it up, and it will only shine those lines which are absolutely perfect polyamide optical signature of material. If my material is in my optical path, it will be lost due to absorption, intensity will be lost. And if I measure simply energy by bolometer, I actually can detect my chemical element because my light source in infrared is tailored with very, very narrow lines. So perfect absorber is perfect emitter. Okay, so very final things. I try to convince you that we know everything how to control metamaterials for surface, for sensing. But the question is always what we sense. And in this particular case, hydrogen. Okay, let's come back to the hydrogen generation story on the surface of platinum, which is the easiest electrode. No any catalyst, photocatalyst is the simplest way. Our argument is that the species which are hydrogen ion, molecular ion, is involved. I'm not going into details, it's another story. And also I should admit I have no university chemistry training, so don't believe what I'm saying. But yeah, this is just introduction slide with the papers we published. Why I like this, we still have training in physics and thermodynamics. So if I look for the published papers in expert groups, they always will see what is happening with the hydrogen emission, hydrogen evolution, which is at 0 volts. If you approach this position, you have 2 peaks, and then you have hydrogen emission. So what is happening if you measure mass changes on your electrode? There are 2 steps which are equal. So mass is changing, and this is equal, and you have these 2 peaks which have different, it's twice different areas. How people are explaining this is always atomic hydrogen on the surface, then they are measuring Herovsky reaction. We don't believe it because only this method explains quantitatively 2 masses are going from the surface. 1 electron is keeping this hydronium ion. Then after exchange, another electron is keeping this molecular ion. So you have 2 charges here, 1 charge here, 2 masses which are departing are same. So we explain absolutely perfectly with a very simple Nernst equation, which is for reversible processes. There is no surprises, so these are the formulas which are fitting the hydrogen evolution. This is my belief that people should pay attention. But again, I have no training in chemistry, so this concludes my talk. So we need to know what we are sensing. So what I showed that actually they're very simple nanotextured surfaces. They are perfect for surface enhanced Raman, and we don't really need to do much complicated fabrications. We will not reach the record high efficiencies for surface enhanced Raman. They are good enough for many applications. And if you make them sensitized, actually they work perfect. Then metamaterials, it's really booming field. What I showed here that we create a strong field below particle, and this is causing this Rabi splitting. Rabi splitting means simply you have cavity and absorber, and they are interacting so strong that no light is coming out of your cavity. So Rabi splitting basically can be, if you calculate how much molecules you excite in your sample. So we excite 5-7% of all polyamide below this surface, and then we have Rabi splitting. This is what you expect in this strong light matter interactions. And this is really opening door for quantum optics. And then for hydrogen evolution, yeah, I'm very happy that Manas is driving us into this field. We are trying to understand what is happening in the most simple cases, and this last slides I was kind of teasing you to have a look. Really, we need more understanding how water is split in the most simple case. Okay, so contributions, it's most of collaboration is with the Yoshiaki's group in Yokohama. So for him, 100% hydrogen is absolutely safe. There is no oxygen, so we can run experiments. This is our former and group members and current group members. Tanya and Thomas, our engineers in Nanotechnology facility. With Manas, we supervised a joint student, Hani, she just finished. And they're working on electrical sensors. I have this mind of optical sensors. So it's very interesting for me to see what is electrical detection. Then with Paul and Sally, we collaborate for surface enhanced sensors. Yes, so big thanks for our silent friends in the lab. So we have good facility here, and thank you for your attention.
Thank you so much, Saulius, for a very interesting topic. So we have time for a couple of questions. Yes, please. You want?
Very interesting.
So thanks for the nice talk. It was very interesting. I think it's not relevant to the background, your background, but one of the most important basically gaps I see here is about crosstalks with other gases, other vapors. Have you thought about this?
Yeah, well, yeah, the question was clear, yeah. Actually not. So for hydrogen sensing, we really have the fully controlled environment. So when we have different gases, I think for that palladium, platinum type of sensors, and also yttrium and tungsten oxide, they are phase change materials with in reaction with hydrogen. Somehow I have sensitivity in material already. So I was not trying to make my sensor working in difficult environment to putting different gases. So it's actually a good point. But I don't know. Yes, so you should probably select specific gas which can enter the phase. And hydrogen is absolutely specific. It comes also to my last kind of discussion about hydrogen evolution, because molecular hydrogen ion already small enough to have possibility enter the volume phase of materials, palladium. It can be absorbed, and then protons are even smaller. So hydrogen is unique because you can have so small entities of hydrogen species entering the phase inside the volume, and then you are measuring in the volume during transmission measurements. It's really invitation because you have volume, which is kind of sealing everything from surrounding. So, but how another material can enter that phase, I think it's a valid question, and yeah, I have no answer. It's really a lot of experiments already, yeah, but it's a good question.
Any more? Okay.
Yeah. It's just co-sputtering. So it's co-sputtering, you have different bias on your targets, and we have 3 targets in NanoLab here. You can sputter 3 targets if you want, and then you engineer your coating. And we have another stories, we use those Olympic metals, you know, copper, gold, and silver. You can put 3 targets and you can make any permittivity engineered in your coating. But palladium and gold, they're basically the same atoms. So the alloying is perfect, as you saw. Yeah, it's a good question. I think when I showed that our all sensors died in 2 years, probably faster, was because of we suspect sulfur in air, not carbon, but definitely it will be present. But that annealing and aging with the hydrogen low, it's actually recovers sensitivity.
Thank you. I think there's no more time for question, but if you have more questions, even with the online attendees, so please forward it to us. We'll ask.
I'm around.
Yeah.
Ask questions. I can. It's just neighboring building. I can show the lab.